Thanks, everyone. One of the newest it's one of the
Like,
you
oh, you have to do it again.
You have a microphone. Yes,
I think so. Yeah, that's what this is. Is it working or do we need to test? Hello, hello. Hello, hello. Okay. And do I forward on that computer then or mine? Okay. Okay, great. Okay, so we can just like the oops. Okay, cool. That works. Hi everyone. Wow. Hey. Okay, let me get the water away from the laptops because that was a thing that happened to me once, never again. Um, Thank you so much for the invitation. This is really cool. For me, timing wise, this has been really neat because I've been away from universities for a while. I did my undergrad in physics, and then I did my PhD at a place called Scripps Institution for Oceanography. And there were no undergrads there. It was at a university. It's a part of the University of California, San Diego. But the university sits at the top of the hill, and Scripps Institution of Oceanography sits down the hill closer to the water. I'll show you a picture. This is where I like to study the most. As you can see, that's the Pacific Ocean just behind me. Not bad. No undergrads around though, and I wasn't TAing, and so I've just been away from that world. And then as a postdoc, I was at the University of Manitoba, but I lived here. And so once again, I was still away from university until I started working here and teaching a class that I took as a student. And so I've been like revisiting the world of being an undergrad, and it's been super fun. And so when I got your invitation, and I started thinking about all the other things that happened during those years. So thank you very much for the invite. Before I start, can I get a raise of hands of first year students? 1, 2, 3. Second year? 1. Third year? Fourth year? Fifth year? Aw, okay. Cool. Okay, so that's a big mix. Okay, don't be shy. Raise of hands of people who came just for free food. Oh, come on, you can be honest. Okay. Raise of hands for people who are interested in doing research during their undergrad. Maybe that's why you're here. Okay, big chunk. Raise of hands for people who are about to graduate and they're thinking about graduate school and what they want to do. Okay, cool. Okay, I'll try to like touch on these topics and like what it was like for me. Feel free to interrupt me at any time. If you've ever been in my class, you know, I don't like to talk the whole time. I like to just let other people do things and answer the questions for me. So please don't be shy. Right, so this is going to be about my undergraduate years and where it got me. And so I thought I'd start with a photo of a cool place it got me. So this is taken in Svalbard. You have probably no idea where that is. I've never heard of it. Raise of hands of people who know where Svalbard is. I got one. Amazing. Can look it up later. It's like north of Norway. It's actually in the Arctic Circle. It was my first time in the Arctic Circle. And I was invited there to give some presentations for a graduate winter program. It was crazy. It was meant to be a winter program. COVID happened. It was a summer program, which meant that the sun was up the entire time, which is crazy. So we had a big party at the end, and I walked home at 3 a.m. and it felt like the afternoon. It was wild. But anyway, and this is my first time seeing actual sea ice because I get horribly motion sick. So I do all of my oceanography from the office. Okay, so that's a bit of an intro. I have no idea how long this is going to take also, so please just, yeah, keep me on time. If you guys are getting bored or whatever, send me away. So a few things I like to think about. So as I said before, I am a seasick oceanographer, so I like to do all of my work like this, little computer in front of me, ideally a piece of paper because I don't like screens so much. And if it's pretty outside, that's definitely a plus. I'm thinking a lot about the Arctic Ocean and in particular how the sea ice is changing. So this is a nice video from NASA. It's an animation, but based on observations. And you can see the sea ice cover retreating and expanding each season with the summer and the winter. But this is also, if you can see this little number up here, the years going by over the decades. And so we're in the 90s now, and probably by the time I'm done talking about this slide, there'll be much less sea ice there. So my interest is understanding the ocean's role and how the ice is disappearing. So we know we're in a warming planet, and so that means the ocean is holding on to more heat, and the physics of how the ocean's interacting with that ice is changing. And it turns out this is not well simulated by climate models, so there's a lot to do there, particularly right at that ice-ocean interface, and I'll come back to that at the end. But yeah, so that's kind of the gist of my work. I like to sit down, do cartoons, a little bit of math, a little bit of modeling, a little bit of using observations from the Arctic Ocean. But that's not where I started. I started not caring anything at all about any of this. I was a tennis player, and that's all I really cared about. And I was in high school focusing mostly on tennis. So I come from the US. I don't know how much you hear about US schools, but there's a big chunk of them that like you can kind of sleep through it and get great grades. And so I was doing that, and I wasn't caring about school, and I was caring about tennis, but I was getting good grades, so we're cool. And then I took my first physics class, and I got a big fat F on my very first quiz. And that really woke me up. It really woke me up from my sleep, and I found it extremely interesting because all of a sudden I was like, okay, I can't sleep through this. I have to try. And so I got interested, and all of a sudden I was like, I really like this thing, but I'm a tennis player. So that's where my story starts. So I'm in undergrad. This is me for my undergraduate years, and there's an ice cube here, and I'll explain why. It's got nothing to do with sea ice. So I was an undergrad playing tennis. My focus was tennis. I didn't really know what I wanted to do. I thought physics was cool, but I thought the only thing you could do with it was be a physics teacher, which turns out I really love teaching physics, but I didn't know that at the time. And so I was focusing on tennis, and I was like trying computer science, engineering, maybe some journalism, biology. I was like, I don't know, I'll try stuff. But I didn't really care either because my life was about tennis. And then at my second semester there was this patch of ice, and I slipped and I broke my foot. And so my life changed a lot there. It's actually a much longer story than this. I broke my foot, but the doctor thought that the bone was naturally in two pieces. And so I continued to play on this broken foot. And my coach was not happy with me because he was paying me to play tennis. Yeah, so he was grumpy, I was grumpy, and tennis was becoming much less interesting to me. But my physics books, my physics classes, like it was just this amazing thing where everything else would disappear because it was still the hardest thing I was doing. And so I'd sit down and try my physics homework, and just like that whole world would disappear. My foot would disappear, the tennis would disappear, just me and like the math and the physics, and feeling kind of connected to reality at the same time. It was an escape, but it wasn't an escape. It was an escape towards something real. So that's how things started with me. And I was like, okay, I like this. This is cool. And it was interesting. I don't know if you've ever experienced this where you go into a physics class. Maybe you had this at the beginning and you're just like, what am I doing here? Like, there's just these equations on the board. There's this professor that's not making any sense. I can't understand him. And you're like, what the hell am I doing here? I had so many of those. But I don't know, there's just something about it that I really liked when you're sitting in the quiet of your notebook, sorting it out. It just kept going. And I kept getting less and less interested in tennis, more and more interested in physics. And I talked to one of my physics professors about this, and I had heard there are these internships around, which I'm sure you've all heard of these internships around. I said, I think I want to try one of these. And he was so nice to say, yeah, you should do it. And I'm going to tell you how, because I had no idea what I was doing. He was like, go ahead and write an application. Tell me what you want to apply for. And I was like, okay. And I chose one that I thought looks cool. I'm going to apply to it. And I wrote an application, and I pretended that I never played tennis and my life was physics. And I showed him and he was like, wrong, wrong. 10, find 10. You're going to apply to 10. This must have been the last year that we did everything by hand too. So I like getting the letters together and like the envelopes and sending them out. And he's like, also throw out this personal statement and talk about your tennis and talk about how you're going to take whatever tennis skills you developed and now you're applying them to physics. Had me completely rewrite my letter. And then I applied to 10 places and I got into one. So good move to apply to 10. And that was kind of my standard after that. And so my one brought me here the first time I got to San Diego. So that's at UCSD. It was cool. It was very cool. It was a different world for me. This was my first presentation. It was on Big Bang nucleosynthesis. So for context, I had taken the equivalent of 151, 152, and 250. For those of you not in that speak yet, Physics 1 and Physics 2, the intro, and then electromagnetism, the first part. And that's it. And then I showed up and the guy was like, yeah, you're going to do theoretical quantum astrophysics. It's going to be great. And I was like, okay, that's what research is. Cool. And he gave me a bunch of books. And ultimately, what I learned was first that I didn't know anything about anything. But second, I like to sit down and learn all sorts of weird shit. And third, later on, I learned that actually I wasn't super doing research yet, but it was a nice opportunity to get your feet wet. And so they basically were like, she's having fun and she's learning stuff. And I'd sit down, they'd give me a bunch of things to learn every day. And then I'd sit down with a graduate student and ask them all of the questions and tell them all the things that didn't make sense to me. And that was my internship. And then I did this thing and I still remember standing here for the first time and pooping my pants and like breaking like the laser pointer out of nerves. I don't know if anyone can relate to that. So that was my first experience. So that got me here. I did something weird while I was there. So I had at that moment decided to hang up my tennis rackets. I wasn't going to go back and continue playing tennis on my now very damaged foot. And sorry, I should start out. So this was at a place called Binghamton University. And I thought, I have no reason to go back to Binghamton University. I like physics. It's not really a physics school. And I went there for tennis and I'm not going to do that anymore. And I was in San Diego and I was like, and I like it here. I don't want to leave. And so I just kind of stayed and I was invited to stay with a friend's parents' place and help like take care of her brothers for a year. And I just hung out and took classes. It was weird. So anyway, I'm there and I'm just like, I'm just going to continue on this physics adventure. I couldn't stay there because it's very expensive to pay for school in California if you're not a state resident. So it's kind of just like a visit. And then I got to get back to New York where I can afford the tuition. This isn't a Canadian problem, is it? A little bit. Okay. In a very specific, interesting. I'm curious to know more after. So I stayed there and taking classes. I'm meeting all of these physics students, and this was brand new because at Binghamton there were 10 students in the physics major, and in San Diego, I'd say at least 50. Still nothing to U of T level, but I was blowing my mind, and there was all these like physics minors and stuff I couldn't. In my year, yeah, in my year, yep, 10 in Binghamton, 50, and here it's like 200 per year-ish, somewhere in that. Yeah, whole nother level. So anyway, I was there, I'm meeting all these students, and it comes time to apply for the following year. And I'm gonna do the same thing and choose 10. And I've chosen, and I'm like, astrophysics is so cool. I'm gonna just focus on astro. Like that's the coolest thing in the world. I wanna think about the universe and planets and stars and whatever. I don't care. I just want to do astro. And then I met this guy and he was like, you know what? You should also apply to Woods Hole. And I was like, that's a weird place to make up. That's not real. What's good joke. And he's like, no, you should do it. I'm taking a class in oceanography. Just like throw it in there. And I thought, you know what the hell? I'll throw it in. And it was in oceanography. And I remember like it was the one application I barely gave a shit about. Like I just was like in bed and I was really just like, I didn't even edit it. I just kind of went for it. And it was the only one I got in once again. And so that brought me to Woods Hole, Massachusetts. So this is one of the oldest oceanographic institutions. I wish I had some more pictures of this. I just have me like with my friends on the beach and in the water. But it's on Cape Cod. So if you think of Massachusetts, it kind of looks like a gun with a little tail. It's on the tail. So I went from San Diego to Cape Cod. And that was my first go at oceanography. And it was my first go also at starting to do actual research. Like I learned how to program. I was given a data set, and I was said, have at it. And so I was doing these things and it was fine, I guess. It wasn't as dreamy as like reading all the cosmology books and asking about like what's going on and trying to understand quantum without knowing anything about quantum. But, I was like, it's cool, I guess. Water, I don't know. And so I'm there learning, mostly struggling to program. It was not coming fast to me, but I was just like doing the thing, going to work every day. But meanwhile, I had become friends with a professor in San Diego, and he said, while you're in Woods Hole, go to this thing called the GFD Summer School. It's for graduate students, but just go there. Come on in and get a snack. Or not. And so I started going there, and that one stuck. So GFD is geophysical fluid dynamics. And they were calling themselves the mathematicians. And they were just in this little cottage with blackboards all the way around. And it was filled with like 30 desks and chairs that it looks like it's from the 50s. And, and they were doing more things on the theoretical side. They were also doing lab experiments and numerical simulations, but it was more on like they're writing equations, and you could kind of see it. I had no idea what the hell they were talking about because I'd never done any fluid dynamics, but you could go to these talks and see like they're trying to describe the motion of waves and currents and all of these interactions, and they're writing it down with an equation and they're describing it. And there was something about it, even without having any idea what the hell was going on, that was resonating. And so I kept going. And then there was this one talk, and I still remember it, blew my mind. This professor came and she gave a talk on astrophysical fluid dynamics. And so she was talking about, come, grab a snack, but you don't have to. So she was talking about astrophysics. She was talking about the fluid dynamics inside of stars. And so I was seeing all these things that I kind of remembered from San Diego. And it was blowing my mind because she was bringing in all these fluid dynamics concepts. And I was like, that's the thing. That's the thing I want. And so at the end of the summer, I went up to her and I said, can I work with you next summer? And for some reason, she said yes. And this was the thing that kind of set everything in motion to me, was this internship number 3. And for perspective now, so it was between my 4th and 5th year. I needed that 5th year because I had, in between that time, transferred to another university with new sets of rules. I had to take a ton of English classes. It was annoying. And I needed that 5th year to graduate, mostly so I could take English courses, which killed me, but here we are. And so, yeah, that's this part here. So now for some physics. You're not allowed to answer this one, or maybe it's a good test. So this was an interesting project. It could have been oceanographic or astrophysical. And I said, I definitely want astro. Like, I'm sorry, I just think the ocean's boring. And she said, no problem. We're just going to tune the parameters and it's going to be more astrophysical. But I'm going to talk to you a little bit about the physics from the oceanographic perspective. then we'll go to the astral world, and then I'll bring you back to the ocean world. So let's start with this. So I've got a cup of well-mixed water, one salty, one fresh. Which one melts first? Raise of hands for the salty. Okay, close your eyes. Everybody close your eyes. Okay, raise your hand if it's salty. Fresh. Have you seen this before? You were the first group to get this right. Fresh, why fresh? Somebody tell me. I've fooled so many professors with this, but not you. Yes. Because it takes, I thought it takes faster, it boils faster. Like you add salt and then, oh my gosh, that's amazing. Okay, so here's the general idea of what other people think, not you geniuses. We throw salt everywhere, right? There's literally salt all over the ground because it changes the freezing point, raises it. So we're melting all that ice outside. So most people think it's salty, but it is fresh from a completely different reason. And I will show you with a video. There are cats in this video, so you're gonna have to like concentrate. Do your best. So we've got 2 mason jars here. One I've just poured a ton of salt water in. I'm trying to mix it up. It's not all gonna dissolve, but you can see it's pretty cloudy. And then the other one is fresh. And then we've got some blue ice cubes so we can see where the meltwater goes. So this will kind of tell us what's happening physically. So first, the fresh water. And what I want you to notice is that this meltwater goes straight down to the bottom. The salt water, on the other hand, you'll see all that blue stays more at the surface. Can someone tell me why? What is happening here? Yeah. Yeah, that's exactly what's happening here. So here, the density is controlled by the saltiness. So, cat can't see it. So the ice melt is fresher, therefore lighter. It stays at the surface and away from this saltier, warmer water. Why is it going straight down here though? Somebody else? Cold things are denser, exactly. So then this is the big thing with the ocean. We have to think about how density is controlled both by temperature and by salt. So you're exactly right. This one gets protected, and I'll fast forward at the end to prove it to you. So you've got this colder, fresh water here that's protected from the warm, salty water below it. Whereas this one, you're getting convection, just like when you boil a pot of water. Which one do you think is most like the ocean? Salty water. It's a trick question. Answer is both in a way. So in the mid latitudes, the density is controlled by temperature, right? So if we go out to the lake and you go way, way deep at the surface, it's nice and warm. So warmer, lighter at the surface. As you go down, it gets colder. If you go to the Arctic Ocean, on the other hand, the deeper you go, the warmer it will get because it's controlled by salt. Yeah. So it's nice, cold and fresh at the top, warm, salty, and this is water coming in from the Pacific and Atlantic waters. And oceanographers, Arctic oceanographers really care about that because that water is getting warmer and warmer with the decades. And there's enough heat in there that if it were somehow brought to the surface, it could melt all of the sea ice just like that. And that's becoming important because the ice is a lid, acting as a sort of lid at the ocean. So the ocean gets stirred up by the wind, and then the wind will push the sea ice, stirring, stirring, stirring. As that ice disappears, that lid is disappearing. And so it's easier to stir up the ocean. So that's part of the physics that's changing there. Everybody get it? You won't be tested. Okay, onward. How am I doing with time? I can do that. I won't go too far along. All right, so oh, I put it twice. I don't know why. We don't have to see it twice. Okay, yeah, so just a quick cartoon version of this. So on the freshwater side, you have this cold water parcel. It's heavier, comes down, the warm comes up. Mixing, convection, salt water, it's cold and fresh, above warm, salty, that one's stable. Okay, but you can imagine a version of this experiment where something completely different happens. If I take those 2 cups of water, the salty one and fresh one, and now I've put it on the stove, it's temperature that's going to win, right? So if my temperature gradient is strong enough, it doesn't really matter that it's salty. And so it's kind of this balancing act or this fight. So you can think about this as, I won't tell you what all of these, I won't give you it doesn't matter. Doesn't matter. This is basically telling you the gradient, the change in the gradient of, or sorry, the gradient of density controlled by temperature over the gradient of density controlled by salt. And they're competing. You have the unstable component from the temperature gradient when you have warm below cold. And then you have the stabilizing component from the salt gradient. And so if this is really, really big, then you're stable regardless, right? If I put a ton of salt in, well, it'd have to be a whole lot of salt if I'm boiling the water, but you can imagine it's really, really, really salty, I'm stable. On the other hand, if my temperature gradient is huge, the amount of salt, it's not going to matter, it's going to convect. So we've got stable on one side, convective on the other side. Now it turns out there's a third stage right in the middle that we call double diffusive. That's where you get something, double diffusive convection. Has anyone heard of that before, out of curiosity? Yeah, I'd never heard of it either. Okay, so before we go into what double diffusive convection is, I'm going to tell you what single diffusive convection is. So let's throw out the temperature. Just think about the salt water case. So we've got all these little salt nuggets, more at the bottom than at the top because we have a stable gradient. And now we're going to just take this little parcel of water and give it a kick. We kick it up and it brings all that salt with it and it gets to the top, and everywhere it looks around it, there's less salt. It's lighter, it's heavier than everything that's around it. So it falls back down, comes down. Now all of a sudden it overshoots where it started. It's lighter. It's lighter than it was. It's lighter than its environment. So it goes back up. It's more buoyant. Now it's heavier, it's less buoyant. And what you get is an oscillation, just like what we learned in 131, just like a pendulum or a spring, and it's completely stable. It's just up, down, up, down, up, down, something called internal, I think that'd be like an internal wave. Now let's add temperature. So now we take that same fluid parcel and we bring it down. And now this parcel is colder, but also fresher than where it started. So here's the trick. Temperature, it turns out, diffuses 100 times faster than salt. So it brings all this cold, fresh water, but then it quickly loses its cold temperature and becomes warmer and lighter than its environment. And so now it's even lighter than when it starts. And so it overshoots. And then once again, now because it's overshot, it's saltier than its environment. It quickly loses its heat. So it becomes colder, even more dense, and it overshoots again. So now every time with every oscillation, it's going farther and farther and farther until you reach turbulence. So that's double diffusion. Here's where the magic comes in, and the part I love, because it's like, what, why? This mechanism is thought to explain these so-called staircases. And you can see why they're called staircases. They're just these lines, literally looks like you can walk up them. What are they actually? So this is temperature, salinity, and density as a function of depth. So as you go deeper, you're getting saltier and warmer, as you all know, because you're all Arctic Ocean experts. And as you do that, there's a step, 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 step. And there's a lot of ideas as to why. but it's not totally clear. Okay, what's this got to do with astrophysics? Hard to say because we can measure these things. We can measure those steps in the ocean, not measure those steps in the interiors of planets and stars. But here's one idea of how it could be useful. So you imagine, once again, you've got your cup of water and you are going to make it salty. And let's put the same amount of salt in these two cases, but in two completely different ways. One, you're going to sprinkle it in. And of course, as you sprinkle, it's going to stay fairly well mixed. And you're heating, by the way, you're heating these cups from the bottom. So you're just sprinkling it in like you're about to cook something. Sprinkle, sprinkle. The other one, you're dropping a big salt chunk at the bottom. By dropping that salt chunk in, you're setting up your system for double diffusive convection because that big salt chunk is gonna have a big salinity gradient at the bottom. So the comparison is that one of these is double diffusive, one of these is not, and it'll tell you the history of how this is formed. And so the astrophysical analogy here is that sprinkle, 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 that's like planetesimals coming in and colliding to form a planet, versus there being a big chunk of rock or else and an atmosphere forming around it. And the idea is you might be able to use double diffusive signatures of double diffusive convection to sort that out. That's all I know about that because I went into another direction. And I love this. I thought it was very cool, but it was, yeah, well, I'll explain more. Here's my whole spiel for that, which I won't get into, but I was having fun looking at it. It was really cool. You got to do a lot of numerical stuff. I got to derive some equations, test a theory, make pretty movies, and I'll just skip straight to the movie. So I'll start right, I want to pause it in two spots. These little squiggle lines, that's that linear instability that we went through with the different types of oscillations. So that's why you get this vertical motion. And then very quickly, that saturates into turbulence. And I'm gonna just speed this thing up to 2. And what we're gonna see is these layers forming. So these colors, so basically the simulation was starting with linear gradient in composition, which is astro term for salt, can be anything, and temperature. And this is going to be perturbations away from that. And so as you see these different layers form, that's the staircase. Okay, onward. All right. So that was my first science paper. I published first author, because my supervisor was very generous, but I published first author in the Astrophysical Journal. And I thought that was so cool. And I was like, this is it. I'm going to do astrophysical fluid dynamics. I love this. And then I'm going to move this. So then I graduated and then I went to Australia. I found another fellowship. And now I'm no longer really eligible for many fellowships because I've graduated, but there was one you could do after graduating. And it was in Australia, which was so cool. And I went and I had so much fun. I saw kangaroos. I was swimming in the Great Barrier Reef. I had a friend there who had a pet rat, which was super weird. And I got to go to an observatory, which was gorgeous. That's actually where the background photo is, but I've totally covered it, unfortunately. And it was, I mean, I wasn't great staying up all night. I got very grumpy, but it was a really cool experience, except the science was not really resonating with me. I was doing observations. I was looking at observations. I had it was this huge galaxy database of galaxies. And I was running statistics on it. And the words were still cool. I was looking at metallicity and star formation rate and mergers. And the pictures were really pretty, but it was just not hitting me in the stomach. I think I was missing the math. I don't know what it was. Everything else was cool. My supervisor was awesome. But it wasn't quite hitting me. And then I left and I ultimately decided I was going to take a year off, see if I really wanted to do research or something else. And I was in New York City at the time. And this was in 2012, so not too long after everything went to shit and getting jobs was hard. And I tried to get a real job. It was not going well. And I started talking to researchers, and that was not going well because they don't really have funding for non-students. And so, I was just like, okay, I'm just going to be unemployed in New York. I was crashing my boyfriend's place, feeling like a huge loser, getting ready to apply for a McDonald's job. And like, what the hell did I do? Because I had an offer to go to Santa Cruz and do more of this. And somehow I was like, I'm heading to McDonald's. Um, and then I got very lucky at the same time twice. I got a job offer for a social media marketing company, which I was like, okay, that's a job. That's something. And it was weird. I had to take a math test, and I swear it was third or fourth grade math. There was a question on there that said, if the movie starts at 2 and ends at 5, how long was the movie? I couldn't believe it. I was like, okay, it's a job. And at the same time, I was still knocking on doors for research, and I knocked on a door at the Museum of Natural History. And I had knocked on this door a while back, and it was closed. And then somebody sent me to knock on a different door, and it was open. And then there was another door there that was open. All of a sudden, there were two doors open at the Museum of Natural History, and they were both offering me jobs. And Neil deGrasse Tyson was there, which was cool. I don't know if you know that guy. So yeah, that was an easy choice. So I said no to social media marketing and yes to the museum, which is why I have a picture with the dinosaur here, and lots of cool other stuff. And so I did this really cool thing, and I worked at the museum, and it was just like the best perks in the world, because like just literally walking into that museum every day and having a card and getting to like roam around after hours. They even had like a yoga class after hours, so I got to like do yoga stuff with all like the dioramas all around me. And once a month Neil deGrasse Tyson hosted wine parties, and I got to get drunk with Neil deGrasse Tyson. It was crazy. And like we were the same way home, so we even went bike riding with him once down. I know, it's nuts. And my supervisors were help fueling like all of what was going on in the planetarium. So I'd go, I didn't have any real training in astrophysics. I had done like all these internships, but never a class. And so I was going to the planetarium trying to teach myself about my research, and seeing their names on there and like watching the planetarium and show, and just like, wow, it's gorgeous, it's beautiful. And astro, like just literal stars in my eyes. Like it just felt good to be there, and I felt good about myself. Um, until I'd sit at my desk, and I loved the problem solving of it. Like that was cool. I was getting into coding, I was figuring things out. I liked solving the puzzle, but like I'd go to talks, like there was something missing, and I felt like that thing that was missing, it was interesting. So one project was very like theoretical. I was doing numerical simulations, and the other one was all about data processing observations. And it was like they could have been two completely different fields of study, because the stuff that I was doing on the theoretical side, including this stuff, wasn't really testable. And then the stuff that I was doing from observations, like I couldn't really add theory to it. It was just so separate. And so I'm there, and I'm kind of grappling with this. I'm grappling with it being so cool. Like it's just the coolest thing in the world, but it also not hitting my belly like Santa Cruz did, like this double diffusion project did. And so things kind of came to a head. So I applied to 4 places for grad school, and I got into 2. One of them was here with this person, and one of them was here with I don't know who. And it was at Scripps Institution of Oceanography. I didn't go for physics, but I was like, let me just try in the oceanography department. Like, what the hell? And I had to make a choice because they're so different. Um, and honestly, I could have flipped a coin, because either way it was going to be fluid dynamics. But in the end, I went with Scripps. I think in part, you get to go and visit the campus. And I saw this like beautiful ocean. This one, the graduate students, they didn't even have windows in their office. And at Scripps, like it was a room like this for first year. So like windows on all sides, looking out at this. And it just seemed so nice. And it seemed like all these possibilities, even though I didn't know what they were yet. And I just thought to myself, I think I can do this, but I can measure it, but I don't actually know. And so that's where I dove in. And that's where I'm still trying to go. And it's weird. And there's not many people, it's still, I think, many fields, maybe not all, people focus on the observations or they're theorists. I'm trying to put my hands everywhere. So I'll quickly tell you what I do now, and then it's like vacation, so then I'll stop. Does that sound good? Okay, cool. Blah. Okay, so we talked about this. I'm going to move over to the salt-controlled world because that's where I start. So I really wanted to do double diffusion in the Arctic Ocean because we can measure it in the Arctic Ocean. And then I got pulled closer and closer to the ice. So the double diffusion that happens about 300 meters below the ice. And there's a heat flux that comes from it, but it's small. But what I really wanted to figure out was right at the surface, just below it. As I started to dig into this, so my first project was how sea ice is simulated in climate models. And I was like, bad. That's the punchline. Bad, not good. And then the second question is why? So many possibilities. I wanted to think about the ocean. And the thing I started to hone in on was this top layer, this so-called mixed layer. It just means it's well stirred. Like you get a cup of coffee and you pour your cream, it's not well mixed, and then you stir it with a spoon. If you did the same thing, but it was a big tub, you wouldn't stir the whole thing, but you could probably get the surface. Same thing with the ocean, but it's the wind that's stirring everything. This is hard historically to measure in the Arctic Ocean because there's ice there, and the ice doesn't look like this. This looks very fine, like you can just put some instruments in there, but no, real ice, it's jagged. You can have these keels, they're dynamic, so they're smashing into each other. You can have these keels that are extending tens of meters into the ocean. It's tricky to measure because you don't want to break expensive instruments. So historically, the Arctic Ocean, historically difficult to measure compared to the mid-latitudes, but right up near the ice, even more difficult. And then you look at how it's simulated in climate models. You've got all these funky little scales right near our small scale features right near the surface. Centimeters, and they matter because they hold heat and they're melting the ice. Climate models, we just say the top 10 meters is all the same. So there's this big missing piece. And I'm like, I think we can work with that. Okay, so here's just the general idea of what's happening. So you got sea ice, which you know, frozen water, the mixed layer, and then the deeper ocean below. But of course, this ice bangs into each other. Uh-oh, it's not, oh, there we go, good. Bangs into each other, you get these keels. They're like little spoons stirring up the ocean. In the winter, when this ice forms, so when the water freezes, it doesn't hold on to its salt, it lets it go. And so you're leaving behind all this salt as that water freezes, making it saltier, and it convects. And then when this melts out in the summer, that's releasing all that fresh water. And so that makes everything a bit more stratified. Just a quick idea. And now I'm just going to briefly finish up and tell you some of the things I'm doing. So how am I trying to answer these questions? I like to look at climate models, as I already mentioned. I also like to use these really cool instruments called ice-tethered profilers. So these are instruments that are frozen into ice, and they're passively floating all over the Arctic Ocean. They're connected to an 800-meter wire with an instrument running up and down it 3 times a day, collecting measurements, sending it back via text message. Here's the 70s version of that. It's an ice camp, 1970s. People lived there for a year and collected data. Just, you know, they drilled a hole and you lower and raise an instrument. So I love to compare these two things because it turned out this happened in roughly the same location. That location's over here. As you can see, it's changed a lot. And compare these two and see how have ice-ocean interactions changed. The other thing I've gotten really excited about is there's a saltwater pool in Winnipeg, Manitoba, and also Churchill, Manitoba. What a cool semi-idealized setup to study these ice-ocean interactions. So we set up, this is a student I've been working with. He drilled a hole in the ice and was taking measurements this past winter. This is a postdoc working. We put together instruments to measure it. And this is a giant ice cube we made because we thought, wouldn't it be interesting if we could instrument an ice cube and let's dye it. Let's just do like a giant version of these ice cube experiments and throw it in. It was a mess, but we're learning things. On the more idealized side, working with numerical experiments. So this is an ice keel. So this is in the reference frame of an ice keel moving through the top of the ocean. And we've been looking at the effects of the size and speed and what kind of dynamical features you get from that, how it stirs up the ocean. So this will tell you, as the ice is changing, how does that change the mixing? We've been pairing that with this is the first time we did this, some experiments very much motivated by what I showed you before, but now with rotation. So I've got a student who's going to be starting this summer. She's already done a gazillion of these, looking at different rotations, different saltiness, and trying to understand in the most fundamental form what happens with ice melting in a rotating reference frame. We live on a rotating reference frame. And then lastly, this has connected to some outreach I've been doing with students in Churchill, Manitoba, where we did experiments like this with them, except on record players, and then brought them down to Winnipeg and made some giant ice blocks that they could take measurements with in the saltwater pool. And we had a good bit of fun with that, where we just made a ton of also just regular, weird, colorful ice cubes that we got from like cocktail stores. And we made a river too that just kind of had like different colors coming from it. We've enjoyed. And yeah, I'll leave it there. Go on forever, but gosh, let's go already, right? Yeah, so this has been my adventures in undergrad, and I'll just leave it with a few videos. And if you have any questions or just want to chat, I'm around. Oh, thanks for listening to my spiel.
Yeah, sure. Okay. Yeah, any questions?
If you guys have to go, that's fine too. We're a bit past the hour. Yes. Questions? Right. Yes, I'd ask a question. So you kind of started off a lot in astro and then moved more towards the ocean. And I'm guessing from what you described, was a lot of the physics like easily transferable? Like you were kind of doing the same math and similar equations in one context and just switch reference frames? Or?
Yeah, that's exactly right. So what I found, which is interesting, so my favorite class was E&M, and those equations are so similar to fluid dynamics. So if you end up taking electromagnetism, you take a continuum mechanics class, you'll find that there's quite a bit of overlap. You're using a lot of vector calculus. So yes, absolutely.
Would you say maybe there was something specific that stood out that was like wildly different? Or well, I guess there was, but like
wildly different in oceanography compared to other stuff that
it's a silly question, but like I guess out of the things that were kind of similar, what was
wildly different? Yeah, I was surprised how much rotation can mess with your intuition. I would say that was a big one. Yeah, without going into too many physicsy details, but there was a lot of things where it's like, okay, it pops out that there's like this balance. One of the first things you learn, there's a balance between the pressure gradients in the ocean and the Coriolis force. And I was like, pressure gradients, it didn't seem like it was in the right direction. So there are like little funky things that pop out that I didn't think were intuitive. Of course, like the staircases too. Like I think that's what I liked about it too, is you start with something fairly simple, because we do a lot of complicated things in physics, right? Like you go into quantum mechanics and all this wild shit, but you think that the ocean, what could be so difficult? But there's all this shit popping out of there. Had no idea. I mean, turbulence is just a huge, still a huge unknown. Yeah, I don't know if that answers it.
Thank you. Other questions?
So I have a question about the single diffusive oscillation that you mentioned.
Yeah.
So like our atmosphere has a huge temperature gradient as well, right? So does the same thing happen in our atmosphere as well?
Yeah,
And-
absolutely. So you can, gosh, I should have brought it. My partner just the other day filmed.
Yeah.
If you ever see like bands
Uh-huh.
in the sky, that
Like would
you have internal gravity waves. Awesome. Yeah, if you can put that up. So yeah, if you look for bands in the sky, that is considered, yeah, a signature of those types of waves. I'll have one
Okay.
up for you. But yeah, absolutely. Yeah, and it's interesting. So all this stuff, if you go back historically, it's really the atmospheric scientists that start out, right? Because we have this need to know what the weather is. And so that's where things really started, was from the atmosphere. And so all of this geophysical fluid dynamics, for the most part, the oldest version, that's coming from the atmosphere. And then it's slowly being developed to understand the mid-latitude oceans. And then the polar oceans are last, because those are the hardest to get to. But yeah, lots in the atmosphere. And there's lots of people 2 and 3 floors up doing cool atmospheric dynamics as well.
Yeah, so I know you said you did like some astro so the stuff that you're working on with like convection and stuff in the ocean, how is that really like how similar is it to like convection like within like a gas planet or like within like a star?
Yeah, it's a good question. I feel not well equipped to answer it because I didn't go that direction. But the idea was, so basically you take the same equations of motion and we're looking at this regime where you're going more and more inviscid, and you can kind of do these asymptotic assumptions of like, okay, what's happening as we're going and what's the tendency.
I see.
But like you have to keep in mind that these things are hard to measure. But when you're thinking of convection, I would imagine that we understand fairly well. And you'd have to ask an astronomer in terms of how well we understand the temperature. But my memory is they have that down pretty well from the brightness. So in that sense, putting 2 and 2 together, you got it. You know, you can never take a planet or a star and like, you know, put it in a cup and do things
Right,
to
yeah.
it. But yeah,
sense.
but yeah, there's lots of similarities. So this woman that I met, the professor that I met that kind of got me started on that path, she was one of a handful. It turned out there are quite a number of people who have their feet kind of in both worlds, where they're doing things much more on the theoretical side, but you know, they could kind of turn knobs and like,
Right.
now I'm thinking about the ocean, now I'm thinking about astrophysics.
I see.
People to talk to that about. There's somebody here, I can't remember his name. If you talk to Nicholas Grisouard though, that's a good start, and he'll send you to the person. There's a person here I actually emailed when I was an undergrad because he was working in New York City and I was trying to get an internship with him, and now he's somewhere in Toronto or U of T doing similar stuff.
Okay, cool.
But
Yeah.
the name is just like